Good morning, everyone. My name is Lauren McNamara, and thank you for joining Horizon Solutions, a simplified safe distance calculation tool to improve workplace safety webinar hosted by Austin Desmond. We'll get started shortly. We do have a large audience registered today, so to avoid any background noise, we've muted everyone's mics. If at any time you do have a question during the webinar, go ahead and submit that over in the Q&A feature at the bottom of your screen, and we'll get those questions answered at the end of the presentation. This webinar will be recorded, which will be emailed to everyone once we have concluded. And with that said, I'll let Austin kick it off.
Good morning, everybody. My name is Austin Desmond, and I'm an automation specialist with Horizon Solutions. Just wanted to start off by saying thank you all for joining us and taking the time out of your day to come and view this webinar with us. For today's agenda, we're going to start off talking about the need for safety input devices. And we're going to talk about the formula that relates to safe mounting distance, some of the definitions revolving around that, how to find the required information to do these calculations. We're going to run through a handful of examples, starting from the most basic safety relay up through an advanced redundant control logic system. We'll wrap up with a summary and key takeaways, and then spend some time on any questions that come in. Again, as Lauren said, if you have any questions that come in, please use the Q&A feature, as everybody's mics will be muted. So the purpose of a safety device is to stop a hazard by bringing it to a safe state prior to the operator actually reaching that hazard. As you can see here, we have this system set up with a set of light curtains providing information back to a safety relay, which is then tripping the contactor and stopping the press. Now this operation looks safe, and it looks as if it is at a low enough speed. However, oftentimes safety presence sensing devices are mounted where it's convenient, such as on the front of rigid guarding, or on strut work, or on pre-existing fencing, without calculations done to determine if the hazard will actually be stopped in time, or if footprint space could be saved on that machine design by doing the calculations and bringing those safety input devices in closer to the machine in certain cases.
So we're kicking off with our first polling question. That is, what technology does your company use when designing new safety circuits? Your choices are a safety relay, safety PLC, both, or you don't know. And we'll give everybody a couple of seconds to get those answers in. So it looks like 60% has voted, so I'm going to go ahead and end the poll, and I will share the results. And it looks like a combination of a safety relay and a safety PLC are used.
Well, thank you everybody for sharing that info. So now we'll talk about actual safety input devices and how not all of them are going to be equal when looking at individual applications. The main difference here being that no application is ever truly the same as a previous application. Every machine has a unique set of parameters that can cause hazards and need to be protected or designed out. We'll start with object resolution. This is one of the biggest determining factors in using an optical sensing device. So here in the top left-hand corner, we have a set of 450L light curtain sticks. These are set up for what's called finger detection, which is a 14 millimeter resolution. This means that an object with a diameter of 14 millimeters or greater is guaranteed to be detected. This means that you can have the device closer to the actual hazard because we're going to be detecting the hand and the fingers before they approach the hazard, versus something like in the top right-hand corner, we have a area scanner, which is a very nice device and has its use cases. However, you are going to have to stop the machine faster while the person is farther away from the hazard because we cannot reliably detect exactly how close they are to that hazard. This is because these area scanners have a 40 or 70 millimeter object resolution for leg or torso detection. If we can only detect a leg or the torso, we cannot reliably determine how close the hand or the arm or any other part of the body is to that actual hazard. Therefore, we have to stop the hazard sooner. There are also devices that do not use optical presence sensing, such as safe edge and safety mats. These also have many great uses, but also have certain drawbacks. And again, it all comes down to what application you're using them in. One thing to note here is that the smaller your object resolution, the lower what's called your depth of penetration factor is going to be. The depth of penetration factor is how far through an object, a present safety sensing object, you can move through before the output is tripped. So again, in this case, with a 14 millimeter object resolution on the light curtains, we have about a ½ inch depth of penetration. Whereas with a 70 millimeter area scanner, if we're doing leg detection, we may have up to a 3-foot depth of penetration factor based on the arm span of that person. So now we're going to take our first look at the actual calculation based on the ANSI standards for calculating the safe minimum distance. Here, DS is the safe minimum distance. K is the speed constant defined by the ANSI standards of 63 inches per second. This is based on a quick moving arm or hand. An example of this would be if something were to drop off the edge of a machine and someone quickly reaches out to try and grab it. This is where that number comes from. The 3 T's that we see in the equation above are broken out into 3 sections. TS for the total stopping time of the equipment, the mechanical portion of the equipment, as well as the output device. TC, or the control system processing time, and TR is the processing time of the input safety device. Finally, we have DPF, which, as we just discussed, is the depth of penetration factor. This is the maximum travel towards the hazard within the presence sensing device field that can occur before the output is triggered. Now, there's a lot of terms here, but the easiest way to think about this is safe mounting distance is the speed constant times the total amount of time for your input, logic, and output functions to happen in the safety system, plus the depth of penetration factor. We'll move into our first example to begin talking about the most basic form of this calculation. For this, we'll use a SensaGuard door switch, going back to a GSR safety relay as our logic unit, and the output device being a 100 CS safety contactor. Now, if we look in our device manuals, we can determine that the SensaGuard has a reaction time of 54 milliseconds. The output contactor has an opening time of 50 milliseconds. Again, this is model dependent, but here, this is based on the model for our example. And then we have the 440R safety relay, which has a reaction time of 40 milliseconds maximum from a change of input to change of output. Now we'll take all this data and we'll go back to our calculation. We know that K is 63 inches per second, as it is a defined standard. TS, or the stop time of our output, is 50 milliseconds, as it takes 50 milliseconds for our contactor to open up. The control time, here just the relay, is 40 milliseconds to react. And our SensaGuard door switch has a 54 millisecond input reaction time. Since we're using a SensaGuard door switch, the depth of penetration factor is 0, given that the door has to be swung outward away from the hazard in order to access the hazard. We take all those times, we add them together, and we get 144 milliseconds, or 0.144 seconds, and a grand total of just over 9 inches away from the hazard is the closest that the door could be and maintain a safe operating environment. Now let's see what happens to this distance when we look at a slightly more complicated system. Here we are replacing our safety relay with point safety IO that it will be communicating back to a GuardLogix PLC via Ethernet. As you can see, our input and output devices have not changed, so we still have the standard 54 millisecond input time of the SensaGuard and the 50 millisecond output time of the contactor. However, how do we now calculate the reaction time of the Logix system, since it has multiple components and has Ethernet communications involved? Luckily, Rockwell has a calculator tool that they have created in Excel full of macros that will allow you to take data from your Studio 5000 project, as well as data from the user manuals, plug it in, and get a reaction time. So here you can see some of the data that they're actually looking for. All of the highlighted cells are cells that would be your inputs. There are a lot of terms here, so we're going to break them down into a few categories and then go over them. So our three main categories that we can break all of these down into are module properties, the safety task properties, and then the module user manual. These three locations are where you're going to find all the necessary information. Starting with the module properties, the input point delay is the filter setting for safety input devices. This means that any input pulse seen below the filter setting, for example, if you put 40 milliseconds, any pulse shorter than 40 milliseconds will be ignored. 40 milliseconds is just an example and would never really be used in real life, but that is just to get the point across. You will also find safety input RPI under module properties. RPI stands for requested packet interval. This is effectively the scan rate of the safety input. The input connection timeout multiplier, as well as the output connection timeout multiplier, are a calculation for how many packets can be dropped in communications before there is a network fault. The connection multiplier for each of those is just that. It's a delay multiplier. These are also found within the module properties. We'll go over shortly where to actually find these within the individual windows. Moving on to the safety task properties, this is where we would find the safety task period. The safety task period is simply a count of how long it takes maximum for the outputs to be updated within a safety task. We go back to the module users manuals. for both the input and output device, and we will find the input module delay and the reaction time default. Module delay is the max time seen between an input and the change of state of that input, or the change of state of the output and the actual output changing state. The time reaction to fault is simply that. It's typically set lower than the module delay, and if we reach a maximum time or whatever that is set at, you will throw a fault in the safety system. Now let's look and see where we can actually find all this information within the different windows. So if we open up the module properties, we first find the input point delay under Input Configuration tab. This is found by right-clicking on any one of the modules and selecting Properties, then going to the Input Configurations tab. Under the same module properties window, but by selecting the Safety tab, we can now find the Safety Input RPI. Here, set at 10 milliseconds. Finally, if we stay on the Safety tab and select Advanced Connection Reaction Times, this is where we find, for our input and output, the timeout multiplier as well as the network delay multiplier. Here, we're seeing a total packet count of 2 can be lost before there is a network communications error, and before there's a network delay error, 200% of total sent packets must be dropped. If we back out of the module properties and we select the safety task, not the safety main routine, but the actual task, right-click on that and select properties, then select the configuration tab, we will find the safety task period as well as the safety watchdog. The watchdog is not something you have to change. However, it is something that can be changed if you are finding that you have tight communications parameters and you are receiving watchdog failures often. What the watchdog does is takes the safety task period and sets an alarm based on that. So if an output was supposed to be updated within 20 milliseconds and you reach that 20 milliseconds that the watchdog is set at, we've now thrown an error. Finally, we'll move on to the user manuals. This is just a very brief example, but here you can see where we would find the input module delay there of, in this case, 0 milliseconds is the increment that it is set at. This filter setting can be changed. Now we'll move back to our second example. And with all our gained information on where to look for all of these different variables, we've gone out and we've collected all the information. We know what our safety task period is. We understand the task execution time, the amount of time allocated to standard logic, as well as all of our multipliers and RPIs. For the sake of these examples, we're going to assume that the safety project is set up the same with similar properties for all of the following examples. This means that the information on the left-hand side of your screen will not be changing from project or from example to example. What will be changing is the input and output devices, as well as the actual logic devices on the right-hand side. We have the same SensaGuard switch and safety contactor output as we talked about. However, here we're using safety.io modules, which have a slightly slower reaction time compared to other input and output modules. However, you can see they react much faster than a relay. So we'll take all of this information, we'll plug it into our safety estimator. Once all of the data is input, there are a selection of blocks up above that are auto-populated with a macro and give you the required reaction times. For our example, this is a single fault tolerant system, which means we are going to use the row that says considering single fault. And here we're using a reaction time of 115 milliseconds. So now we take all this information, once again, back to our equation. We still have the 63 inches per second, as this is a constant and a standard set by ANSI. We still have our output contactor reacting in 50 milliseconds. However, now with all of the safety logic to process, the Ethernet communications delays, the input reaction time and output reaction time of our point IO, we have come up with a total controls system reaction time of 115 seconds. This is almost triple that of the relay now. Our input device is still reacting in 54 milliseconds, as it's still the SensiGuard switch, which means it also has a depth penetration factor of 0. Plug all these numbers in, and we get a 219 millisecond total reaction time for our safety system. That puts us almost 14 inches, a little over 13 3/4 inches from the hazard. There's a significant increase in distance over our relay solution. Now we'll take a look at a different set of IO with a different input device and see how this changes the system. Once again, we dig into our manuals, into our system properties, module properties, and our safety task properties, and we obtain all of our reaction times as well as all of our logic execution times. Our Lifeline 5 rope pull switch has a slightly lower or slightly higher, longer reaction time on the input side than our SensiGuard does. We're using the same 100S contactor, so we have the same output reaction time there. However, we're using new 5094 Flex 5000 here, which has a very fast reaction time of 6 milliseconds and 4.5 milliseconds for the input and output respectively. Once again, we simply go back to our calculator, plug in all of the logical requirements, and we come back to our calculation with what we found. Same 63 inches per second, the same output reaction time of 50 milliseconds, but now our reaction time that we gathered from the safety estimator was 104 milliseconds. This reduction in time is due to the high speed of the IO as well as the speed of the output. Our lower speed input of 60 milliseconds, but yet again a depth penetration factor of 0 because your e-stop device is not a present sensing device. Therefore, there is no depth of penetration factor. When we add all of these up, our reaction times of 60, 104, and 50 milliseconds, we get 214 milliseconds or 0.214 seconds and a total of 13 and almost a half inches. So slightly closer than our previous system, but still much farther than the relay-only system. Now let's look at a pair of control logics with a pair of safety inputs and outputs, each controlling its own separate device. We've gone back to the same SensaGuard safety input switch with the 100 CS contactor output. But now we're dealing with two sets of point IO and two Guard Logix PLCs. Again, none of the information on the left-hand side of this chart has changed. However, what we can see here is that we have to take into account the input and output modules, reaction time. However, as you can see, we only have to account for one of each because of the fact that the input device is on one and the output device is on the other. If there were multiple input devices, we would have to account for multiple modules. Here, we have to add in a second safety task period. This is because of the second controller. We also have to add in the safety task watchdog timer because of the fact that there are multiple PLCs in the system. Once again, all of this information is taken and plugged into the estimator, which is very simple, straightforward to use, and we get our outputs. Same 63 inches per second, the same 100 CS contactor has a 50 millisecond output time, but now we have 157 milliseconds of logical processing time between PLCs as well as between the I/O. This means we have 261 milliseconds of total system response time, which pushes this system out to almost 16.5 inches away from the hazard. Again, I know we're talking a max difference of less than 7.5 inches between the relay solution and this solution. However, 7.5 inches around the entire perimeter of a machine, if you are safeguarding on all sides, will be increasing your footprint by over 1.5 feet in every direction. Finally, we'll move on to System 5. This is moving back to a single PLC with, again, point safety I/O. Our input device this time is a 450L light curtain, and our output device is a drive. And this is not just any drive, this is a Kinetics 5700 servo drive with advanced safety. This allows for us to do a few things. The reaction time of our light curtain is very, very quick. The reaction time of our input module is the standard 16.2 milliseconds. Where things change is we don't have to wait for the logic to be completed in the PLC and deal with that processing time. Instead, we use the STO reaction time and allow the drive to handle the output function. This means our drive acts partially as our logic device. So now we plug all of this back into our calculator once again. And because our output device is actually acting partially as our logic device, we use a stop time of our output device of 0 milliseconds. And we incorporate the drive's reaction time into the logical reaction time. This means we only have 119 millisecond reaction, plus the 15 milliseconds of our light curtain with a 1/2 inch depth of penetration factor, as we talked about before, because this is a 14 millimeter light curtain. And we are actually 8.9 inches from the hazard, the shortest distance yet. So one thing that I want to emphasize here is that just because a system has added complexity and added flexibility doesn't mean it has to hinder you or slow down production. So finally, some key takeaways. The most important thing here is that operator safety is key. That really is the biggest thing here. There are a lot of times where we see machines that have had safety retrofitted to them in a way that was quick and convenient, and it looks good because now there are safety devices on the machine, but that doesn't necessarily mean that under worst case operation, you're actually protecting the operators and employees. To that point, safety always performs best when it's brought to the front end of the design. Safety always works best when you design it in rather than put it on retroactively. Per the ISO and ANSI standards for machine safety, a safe mounting distance calculation must be done when mounting any presence sensing device for a new machine. Once again, the added flexibility of a system can sometimes drastically increase the footprint of a machine. That being said, the advances made in our safety devices mean that that doesn't have to be the case. If you sit down, think about it logically, plan it out from the beginning, you can design a machine with a small footprint, advanced safety, and truly protect your operators while not reducing productivity. Now we're going to move on to a final polling question.
Yes, it's time for our second polling question and our last polling question of today. And we'd like to know, does your company require the use of safe mounting distance formula when adding presence sensing devices? You can let us know yes or no in the poll I just launched. And we'll just give everybody a couple more seconds to get those votes right in. So it looks like about 65% has voted. So I'm going to close the poll, and it looks like the majority does use the formula. But if you're going to start using the formula after this presentation, feel free to let us know, in an email afterwards.
Thank you, Lauren. And yes, please let us know. But I do want to point out, based on this poll, that means 40% of you are not required to perform this calculation, which means most likely you're using whatever is convenient. Again, that is not necessarily, in every case, a problem. A lot of times there are convenient struts and hard guarding that is far enough away that can be tested and made sure that the machine is safe. That being said, according to the standards, this calculation should be done. And that is all I have for you guys today. I'm hoping that you guys have been sending in some questions in the Q&A, and if you have not and you have any, please do that now. I just want to thank everybody once again for attending and let you all know that the next webinar in our series will be coming on the 20th of August and will be hosted by Joe Amarise. He'll be hosting a webinar titled The Ethernet Switch Technologies for the Plant Floor, and we'll be covering different topics such as the selection of switches, managed versus unmanaged switches, as well as embedded switch technology. Through this webinar, you'll be gaining a better understanding of Ethernet switch technology, as well as the best practices for using them in your facility. And again, if you have any questions at all, please enter them in the Q&A, and if you think of them later on, feel free to send me an email. You should all be receiving a copy of this webinar, as well as access to the examples you have seen within, as well as the calculator and a few other things.
Thanks for a great presentation, Austin. We actually did have some questions come in over the Q&A, so I'm going to just jump right into those. The first one was, why are calculations always done in the worst case?
So calculations are always done at worst case for a couple reasons, but the largest reason being that nothing ever works perfectly. There will always be times where there is mechanical slop, where there is degradation through use. There will always be machines that don't run perfectly. And if you perform all your calculations at average or at best case scenario, the likelihood of someone injuring themselves, especially as time moves on and that machine degrades, wears, things like that, you're not truly protecting the employees at that point. Doing it at worst case ensures that through multiple faults, through a slowed down machine, through communications issues, you will still have a safe machine.
The second question we received was, do I need to change my current machine safety system, or am I grandfathered since I've had this in place for a long time?
So thank you. That is a very good question. As I mentioned on the last slide, per the standards, depending on which ones you follow, they're worded slightly different, but they're both have the same main point that anytime a machine is changed from its original design, that could be a different PLC added, that could be a program changed, that could be as simple as adding new push buttons, changing the IO voltage, anything that changes the original function of that machine or the original design of that machine. At that point, you should be performing a risk assessment and then also, if needed, to come up to the appropriate standards. When you're adding those devices, yes, you do need to go in and use this calculation.
The third question we received was, in the example using a PLC, you used the single fault time from the first column. Why? What were the other three columns showing?
Very good question. So there are multiple columns there. And actually I'm going to go back a few slides here to show it. So when using the input portion, each of these columns can be utilized. So the column with the yellow, those are the inputs, your general inputs. However, to the right of those columns, you could change the white cells that are in line with those yellow cells and compare multiple devices, multiple safety systems. You could also compare multiple RPIs. So if you notice, your safety input RPI there is 6 in our first column versus 8 in the next, 10 in the next, 16 in the following, and 20 in the final. So as the RPI were to change, you can set the safety RPI there. But if you wanted to compare multiple RPIs or multiple input filters, multiple output delays, mimicking looking at multiple different devices, you could then take those and look at that output function. And the first column would line up with the first column, the second column would line up with the second column, so on and so forth. So it allows you to either look at multiple input speeds, multiple RPIs, or multiple device configurations. Does that make sense and answer the question?
They can let us know in the Q&A feature. Someone else would like to know, do these calculations apply to hard machine guarding?
Also another good question. These particular calculations do not. There are ANSI standards that do have a handful of calculations. I believe there's 3 total calculations for hard guarding. But effectively, what all of the standards say is that if you cannot touch the hazard over, under, or through the hard guarding, then it's far enough away from the hazard. So as an example, if you had wire fencing surrounding a robotic arm, that robotic arm is moving around fast enough to severely injure a hand or an arm or a person if it got in the way. If you've got fencing that has, we'll say, let's go to extremes here, 4-inch hole in it. Not everyone, but a large amount of people would be able to fit their fist and most of their arm through that hole. That means whatever that length is plus a safety factor, is how far you have to be away from the hazard with the hard guarding. Go back the other way as an extreme. If you have an aluminum strut construction, so like a 40-20 or something like that, and you have Lexan with no holes in it, you could be millimeters from the hazard. However, you probably don't want to be quite that close in case something breaks, and then you could have something coming through the Lexan.
Regarding the grandfathered equipment, someone would like to know, is that an OSHA requirement that they need to do a risk assessment and improve the safety per risk, and if they do modifications?
I don't believe it is an OSHA requirement. I do not believe so. OSHA cares that the machine is safe, that there's no no exposed wires, no uncovered motors, general condition of the machine. However, they lean on ANSI and ISO for the actual machine safety standards. I believe it is an ANSI standard that says anytime the machine is changed from its original state, a risk assessment should be done.
That's correct, Austin.
Thank you.
Just want to remind everybody, if you have any questions that haven't been answered, you can put those in the Q&A feature at the bottom, and we'll give a couple more seconds to let those come in. If not, this will be our last question for today. And the question is, how can this all be done if our safety task is not complete?
So there are a couple ways that this can be done. However, Rockwell does provide a nice document, and it's actually included, I believe, with the selection of items you will be getting to download here after the webinar. And it's a nice little lab that walks you through and explains all of the default settings for a safety task. If you utilize the default values for the safety task, this can get you started in your design. However, when doing that, oftentimes you should apply a safety factor into that. So by running through this without at least a basic idea of what your safety program is going to look like and do, you could be very far off when it comes to how far your machine needs to be from the hazard. So I always try and encourage a rough program. It doesn't have to include everything, but if you have all of your devices into the IO tree, if you have a general idea of your safety system scan time, then you can get very close and not too much else will change from there.
Thank you, Austin. I believe that's the last question for today's webinar. Thank you, everybody, for attending. Austin, do you have any closing remarks you'd like to make?
No, just once again, thank you all for coming and joining us. We appreciate it very much. We hope you learned a lot, and we hope to see you again on August 20th with Joe Amarise for Ethernet switch technologies on the plant floor.